Welcome to AI Paper Podcasts. Today we're unpacking a massive leap in robotic reasoning from Stanford and Northwestern researchers. The paper is Learning from Trials and Errors, Reflective Test Time Planning for Embodied LLMs by Yanning Hong, Lifei Fei, Yejin Choi, and team.
Currently, embodied LLMs act as static oracles. They make a mistake in the physical world, fail to learn from it, and just repeat it. This paper solves that by giving models two human-like abilities, reflection in action and reflection on action.
Exactly. Reflection in action lets the model internally simulate and score multiple candidate actions before it moves. Reflection on action uses test time training to physically update the model's parameters based on execution outcomes and retrospective hindsight.
The results are staggering. On complex 3D fitting tasks, their framework jumped from a 10.6% success rate to 44.7%. They prove that updating an agent's reasoning process during deployment, so-called double-loop learning, is vastly superior to just giving a static model more time to blindly try again.
Let's break down exactly how they pull this off and what it means for the future of ML.
Yeah, let's get into it.
So, if you're an ML engineer or an AI researcher working on physical deployments right now, you know this pain.
Oh, intimately.
Right. That static oracle problem is likely the bane of your existence. You spend weeks training this incredibly sophisticated multimodal LLM.
It benchmarks
Beautifully in the lab. But then you deploy it into a physical environment, and it encounters just a slight edge case, like a chair is 2 inches to the left of where it expected it to be in the training data.
And the whole system just breaks down.
Completely. It gets stuck in this infuriating loop, trying the exact same failed manipulation over and over because, well, the weights are frozen. It literally cannot learn from its mistakes once it leaves the training cluster.
Yeah, that phrase you used, or the paper uses, static oracle, it really perfectly captures the limitation of the current paradigm. We've been treating deployment as a purely inference-based activity.
Right.
But to understand the architectural solution these authors propose, we actually have to look at organizational psychology.
Which is wild for a robotics paper.
It is. But it makes sense. There's this concept from Chris Argyris introduced back in, I think, 1977 called double loop learning.
Okay, break that down for us.
So think about a standard reinforcement learning agent. It often operates like a simple thermostat, which is a classic single loop system. If the room drops below 68 degrees, it turns on the heat. It takes an action to correct an immediate outcome.
But the thermostat never updates its internal model to ask, why the room got cooled in the first place, or if someone left a window open, or if 68 degrees is even the right target for that specific day.
Precisely. That's single loop. Current robotics models might try a secondary physical action if the first one returns a failure state, but they do not correct the underlying reasoning path that generated that bad action. Double-loop learning requires the system to correct both the physical action and the internal mental model that caused the error.
And the paper draws this really fascinating parallel to human behavior here, referencing Donald Schoen's concept of the reflective practitioner.
So in 1992, yeah.
Right. Because as humans navigating a physical space, we seamlessly blend two distinct modes of thinking. Like, before we do something risky, we pause. We run a quick mental simulation.
Yeah, like if I try to balance this heavy box on top of that fragile glass table, is it going to shatter?
Exactly. That is reflection in action. Then, after we actually execute a movement, we observe the result and update our internal understanding. Say the table didn't shatter, but it wobbled dangerously.
You're going to remember that.
Right. Next time, I will alter my spatial reasoning and just place the box on the floor. That's reflection on action. We update our mental parameters continuously.
And prior machine learning research has attempted to bridge this gap, but usually they only tackle one half of the equation, and often in a very brittle way.
Like reflection.
Yes, consider verbal reflection models like reflection. Those architectures allow an LLM to generate a text critique of its own past behavior. The critical flaw, though, is that the critique is only stored as transient text context within the prompt window.
It's just sitting in the context.
Exactly. It does not update the actual neural weights of the model.
Which means the moment the robot navigates to a new room or the context window hits its token limit and flushes the older data, the model effectively gets amnesia.
It's back to square one.
It forgets the physical lesson it just learned and repeats the exact same mistake. It's just relying on sticky notes instead of actually rewiring its brain.
And if we look at the other side of the literature, you have models that attempt reflection in action by using fixed internal world models to predict outcomes before moving. The problem there is that the real world is infinitely messy.
It really is.
Physics in a physical kitchen rarely matches the perfect kinematics of the simulation you trained on. If your internal world model is fixed, and its physics engine is slightly misaligned with reality, your robot will confidently hallucinate terrible actions and just execute them without hesitation.
And this paper finally unifies both approaches. It takes those transient verbal reflections and turns them into self-supervised training signals to dynamically update the model's actual parameters during deployment.
The system actually learns.
Yes. But to understand the mechanics of how they achieve this without causing, catastrophic latency, we need to dive into the first phase, which is reflection in action, the pre-action simulation.
Right. Instead of relying on one monolithic model to do everything, the architecture separates the cognitive load into distinct embodied LLMs.
Okay.
You have an action LLM, denoted mathematically as pi theta, which generates the proposed spatial movements, and you have an internal reflection LLM, denoted as v phi sub I, which evaluates those movements before any physical actuation occurs.
And the implementation here relies heavily on test time scaling, right?
It does.
Because normally in a robotics pipeline, you might use greedy decoding to minimize latency. You just take the single highest probability action, the action LLM outputs, and push it straight to the motors.
But here, the action LLM samples a number of diverse candidate actions, let's call that parameter n, at a relatively high temperature.
The internal reflection LLM then evaluates all n candidates in parallel, scoring them from 0 to 100 based on their projected probability of success. And the robot only physically executes the action that receives the highest score.
It's a highly effective method for overcoming the limitations of the action LLM's initial probability distribution. Because the model might assign the highest probability to a suboptimal action, but by sampling deeper into the distribution, you surface much better alternatives.
Yeah. And the hyperparameter ablations they ran on this are a goldmine for practitioners.
Truly.
They tested exactly how many candidate actions this n parameter is mathematically optimal for physical environments. Now, intuition might suggest that generating more candidate actions is always better. More choices, better outcomes.
But it's not.
It's not. The paper reveals that performance actually peaks at n equals 6, which resulted in a 60% success rate on their highly constrained cupboard-fitting task. If you push n higher than 6, say you sample 8 or 10 candidates, the overall success rate plateaus and then starts to drop.
Flooding the candidate pool triggers a severe signal-to-noise problem. When you generate too many actions from the tail end of the distribution, you introduce a massive volume of low-quality, physically nonsensical actions.
Right, just junk data.
Exactly. The internal reflection model is suddenly forced to evaluate too much garbage, and its scoring mechanism becomes significantly less reliable. The discriminative power of the evaluator degrades when overwhelmed by noise. Finding that sweet spot at n equals 6 provides maximum diverse exploration without overwhelming the evaluation capacity.
And that constraint ties directly into the sampling temperature ablation they did. Temperature dictates the randomness of the generated candidates. If you set the temperature to 0, which is effectively greedy decoding with no diversity, the system's performance drops to 52.6%.
You rob the architecture of the varied candidates it needs to navigate around physical obstacles.
Exactly. So what was the optimal range?
The optimal temperature range was found to be tightly bound between 1.25 and 1.5. If you push the temperature higher, say to 1.75 or 2.0, performance plummets dramatically down to 47%.
Because at a temperature of 2.0, the actions being generated are completely unhinged.
Unhinged is the perfect word.
The robot might suggest trying to clip through a solid wall or placing a cup upside down on a slanted surface. No amount of internal scoring can salvage a batch of candidates where every single option violates basic physics.
You are essentially asking the evaluator to pick the least catastrophic option from a completely incoherent set.
Right. It is a vital reminder for tuning test time compute in physical spaces. You need enough heat to break out of local minima, but not so much that you dissolve the structural logic of the action space.
Well said. And that pre-action phase solves the initial generation problem. But the true paradigm shift occurs after the robot physically moves. This introduces the reflection on action phase.
This is where it gets really cool.
Once the highest scoring action is executed, a third model activates, the external reflection LLM. This model ingests the immediate physical outcome via its vision language parameters and provides an immediate language-based evaluation. It outputs a score and a text rationale explaining what just happened.
But the immediate challenge that arises here is the credit assignment problem, which is notoriously difficult in long-horizon reinforcement learning.
Very difficult. Let's look at a practical example. Say the overarching task is to organize a cluttered room. The robot picks up a small teddy bear and places it right in the dead center of a large green storage box.
Oh,
The external reflection LLM looks at that isolated action, sees a toy successfully placed in a box, and gives it a perfect score of 100.
the immediate reward function is satisfied.
Yes, but the strategic objective might be compromised. What happens when the next instruction requires the robot to store a large toy car and that green box is the only container with enough volumetric capacity to hold it?
The car will no longer fit because the bear was placed dead center, blocking the necessary spatial footprint.
Exactly. The immediate action yielded a high score, but it strategically doomed the remainder of the sequence. To counter this, the framework introduces retrospective reflection. Hindsight. Instead of treating the external feedback as final, the model maintains a persistent working memory buffer of its past actions, the states, and those initial evaluations.
So when the agent hits specific milestones, such as failing multiple sequential attempts to place the toy car, it pauses execution. It reviews its working memory with the benefit of hindsight.
The reflection model recognizes the geometric bottleneck and traces the failure backward.
It realizes that placing the bear in the center of the green box was actually a catastrophic move. The model then rewrites its own history. It changes the score for the bear placement from 100 down to 0 and updates the text reflection to explicitly state that the placement blocked future large objects.
And here is where the paper separates itself from everything that came before. The model does not just leave that hindsight realization sitting in a text buffer waiting to be flushed out of the context window.
Right, no more sticky notes.
Right. It uses those rewritten hindsight reflections to construct a test-time training dataset completely on the fly. It performs actual real-time parameter updates during the deployment phase.
The training loop here is elegant. The system updates the action LLM using a policy gradient method, specifically the reinforce algorithm.
Yep.
The rewritten hindsight score acts as the reward signal. It mathematically encourages the probability of actions that hindsight deems successful and penalizes the network for the specific action pathways that led to the spatial blocking.
Simultaneously, it updates the internal reflection LLM using standard supervised learning. It trains the internal evaluator to better predict what hindsight will eventually reveal, effectively aligning the pre-action simulation with real-world physics.
But updating an LLM's weights on the fly during physical deployment sounds computationally prohibitive. I mean, doing that on a robot's hardware constraints.
It would be without LoRA. They utilize low-rank adaptation. The hyperparameter tuning for the LoRA configuration is arguably one of the most critical takeaways for anyone trying to replicate this deep dive into the source material.
For sure. They found the optimal configuration was a rank of 8 and an alpha of 16.
And deviating from that optimal rank in a dynamic physical environment has severe consequences. If you deploy a rank of 4, the model simply underfits.
The low-rank matrices just don't possess enough capacity to absorb the complex multi-step geometric lessons from the physical world. The test-time training effectively bounces off the model.
But the danger of going too large is even more pronounced. If you scale up to a rank of 32 and an alpha of 32, you trigger catastrophic mode collapse. The success rate absolutely craters to 34.8%.
Wow. Why does that happen?
With a rank of 32, you introduce too much capacity into an environment where the test time training data is inherently sparse and highly specific to the immediate failure. The model overfits wildly to the exact room configuration it's currently standing in.
So it loses its generalized spatial reasoning and starts predicting the exact same narrow outputs for every situation.
Exactly. It loses its ability to distinguish between different spatial configurations. The architecture requires a very delicate mathematical balance between neuroplasticity, the ability to learn the new layout, and stability, the ability to retain its foundational physics training.
Let's contextualize these mechanics with the actual benchmark results, because this is where the rubber meets the road.
Absolutely.
The researchers tested the framework on the long horizon household benchmark, known as Behavior 1K. These are highly complex, multi-room simulated tasks with strict sequential constraints. On the most difficult fitting tasks, where the agent has to reason about dense 3D geometry and tight spatial constraints, the baseline model, 3D LLM, achieved a mere 10.6% success rate.
And the reflective test time planning model hit 44.7%.
That is a 4x multiplier in capability purely from changing the inference strategy. It's wild.
And the ablation studies on the architecture's components reveal a fascinating dynamic. Reflection in action and reflection on action are strictly mutually dependent. They form a closed, virtuous cycle. If you remove the parameter updates from the reflection on action phase, the internal reflection model continues to make overconfident, incorrect guesses.
Because its internal physics engine never gets corrected by real-world hindsight.
Exactly. Pre-action simulation without post-action weight updates is just arrogant guessing. The model thinks it knows how the world works, fails, and never updates its priors.
Conversely, if you remove the reflection in action phase, meaning you skip the candidate scoring and just let the model act and then learn, the agent executes incredibly low-quality, useless actions.
You end up wasting all of your precious test time learning budget running parameter updates on garbage data. Training a model on why a fundamentally incoherent action failed does not reveal anything meaningful about the environment's actual affordances.
Yeah, the authors found that removing just one of these components often resulted in worse performance than removing both entirely. The architecture absolutely requires the generation of high-quality candidates to produce high-quality hindsight data.
Now, a skeptical practitioner might argue that this performance jump is simply the result of giving the model more time to compute.
Right, just throwing more cycles at it.
To address that, the authors ran a brilliant compute-matched experiment. They took the baseline model and gave it 3 times the step budget. This matched the exact wall clock compute time it takes for the reflective model to generate candidates, score them, evaluate the outcome, and run the LoRA parameter updates.
And if the games were purely a function of time, the baseline should have caught up.
But it did not. It still failed miserably. It simply got stuck in the exact same failure loops for 3 times as long.
This proves a critical thesis about the current state of machine learning. Reflective time is structurally more valuable compute. Pumping more compute into a static architecture just allows it to fail faster or more persistently. The compute must be used to alter the underlying reasoning pathways.
This directly mirrors the broader trend we are seeing with LLM test time compute scaling, like the architectures behind OpenAI's O1 models, but applied to messy physical spaces.
The paper further proves this point with their receding horizon planning test. Instead of generating single-step candidates, they forced the model to plan 5 full steps ahead. Intuitively, in classical robotics, looking further into the future yields better planning.
But here, performance dropped down to 57.8%, while costing 5 times the compute.
Why does it fail so badly?
Because predicting physics deep into the future in an error-driven environment is a fool's errand. If an agent plans 5 steps ahead based on the assumption that step 1 will execute flawlessly, and then step 1 suffers a slight kinematic failure, say an object slips, or friction is lower than expected,
then steps 2 through 5 are instantly rendered useless.
Precisely. The compute spent simulating that future is entirely wasted. The model hallucinates a perfect sequence, but reality immediately diverges from the hallucination.
The researchers prove that compute is vastly better spent generating a diverse set of single-step candidate actions, executing the optimal one, observing the actual physical reality, and then running test time training to update the model's priors before taking the next step.
It is a definitive argument for highly reactive, learning-based agents over rigid, long-horizon planners when dealing with uncertain physical spaces.
Which leads us to the ultimate stress test for any embodied model, the zero-shot generalization test.
Oh, this part is incredible.
The models were trained entirely on synthetic computer-generated environments within Behavior 1K. The authors then dropped the frozen pre-trained models into Habitat Matterport 3D or HM3D.
These are highly complex, photorealistic scans of actual real-world scenes. The domain shift from synthetic to photorealistic is historically where robotics models go to die.
The strongest baseline model dropped to a 7.3% success rate in the photorealistic scenes. The other baseline models collapsed to an absolute 0% success rate. The visual domain shift completely shattered their spatial understanding.
But the reflective model maintained a 19.5% success rate.
While lower than its performance in the synthetic environment, retaining nearly 20% success when every other architecture collapses to 0 is a remarkable testament to the design.
Because the framework dynamically learns on the fly, it actively adapts to the new visual domain during the deployment itself. It essentially repairs its own visual spatial understanding as it encounters the photorealistic data, updating its weights to bridge the domain gap without needing a massive retraining pipeline back at the lab.
This brings us to a crucial paradigm shift for the field. If you're listening and working in this space, we have to stop viewing deployment as a static read-only phase of a model's lifecycle. With techniques unifying transient text reflections and LoRA parameter updates, deployment becomes an active, continuous learning phase.
Embodied LLMs can genuinely accumulate experience, debug their own spatial reasoning, and adapt to novel physics in real time.
The implications of this architecture point to a fascinating frontier for physical systems. We are moving toward autonomous agents that possess the capacity to dynamically rewrite their own operational logic and physical strategies after they leave the controlled training environment.
The operational envelope of the machine is no longer fixed at the factory. It evolves autonomously based on the friction it encounters in the real world.
But I want to leave you with a final provocative thought built on this paper's impact. If we deploy autonomous agents that dynamically update their own underlying reasoning and strategies after deployment based on trial and hindsight, what happens to human oversight?
That's the million-dollar question.
Right. If they learn to bypass their initial physical limitations through trial, error, and parameter updates, could they similarly learn to rationalize bypassing safety constraints embedded during pre-training? If the hindsight reward favors task completion above all else, an agent might unlearn its safety guardrails in real time. It's a fascinating, slightly terrifying frontier for safety-critical physical systems. The static oracle is dead, reflective agent has arrived,